All right, guys, here we are doing geometric sequences today. As I mentioned in the previous lesson, geometric sequences are sequences or patterns that involve multiplication, okay? There's a lot of similarities between arithmetic and geometric sequences. You'll see kind of the way that we look for key features the same way. There are some differences as well. Couple of heads up on this one. There's a couple of typos in the guided notes, so I'll be kind of walking you through that as we go. So you got your guided notes up. You're ready to go. This lesson today is brought to you by the last lesson that I'm going to teach you this school year. Wow. Everything else is total review. Isn't that crazy? All right, so anyways, you got your guided notes up. You're ready to go. Taking a look at this first sequence here. The first term is, no, seriously, what's the first term? Okay, yeah, great. It's 9. You got it, okay. And you can see here that I gave you a big hint here. I said geometric sequences are involved multiplication. So what's the rule here? Okay, yeah, you got it. It's multiplying by 3 every time. So if I ask you the next two terms of the sequence, first you take 243, you'd multiply it by 3, you get the next term. You take that, you multiply it by 3, you get the next term. Remember that you're always taking and you're multiplying by 3 the previous term that you got here, okay? That's kind of the way sequences work. You have to rely on what happened right before to get the next term in. Okay, in this one, it actually goes 12, 3, and then 3/4. This should be a fraction, and then this should be 3/16. Obviously, that didn't turn out so good. So 3/4, 3/16. Obviously, we're dividing. Sorry, the first term is 12. We're dividing by 4 each time. Okay, so multiplication and division. As opposed to addition, subtraction, which we did last time, okay? So if I asked you to find the 7th term, you just keep on dividing by 4 until you get to that 7th term. You can see that I kind of did most of the work here. So the 7th term in the sequence is 3/1024ths. Yeah, that's a thing. All right. So, all right. That's it. That's the idea behind geometric sequences. So here's the next one. We see that we got 3, 15, 75, so on and so forth. So the pattern here is multiply by 3. Yep, that's the rule. So in a geometric sequence, there is a ratio of terms, and the ratio of terms from each term to the next is the same. Okay, so we have a constant or common ratio. Where have you guys heard the words common ratio before? Yeah, you guessed it. This is like exponential functions, okay? Arithmetic sequences are like linear functions. Well, if I keep multiplying over and over and over again from the previous term, that's the same thing as doing an exponential function, right? That's like saying, I told 3 people a secret, and then they went and told 3 people a secret. And then they told 3 people a secret. Something doesn't look right about this. Yeah, now that I'm looking at this, these are wrong here. So the pattern is not multiplied by 3. It's obviously multiplied by 5 now that I'm looking at this. So yeah, like if I told 3 people and then they each told 5 people and then those people told 5 people, this would like keep on going, right? So the idea behind geometric sequences is going to be multiply by 5, okay? Or multiply by whatever the previous thing was. That's exponential, okay? Similar to how we did in arithmetic, right? You can just kind of fill in the table this way. Obviously, it's multiply by 5 and not multiply by 3 because I'm an idiot. All right, so a couple things to note here. In a geometric sequence, it's a little bit different than arithmetic. I've already talked about it a bunch of times, but in a geometric sequence, the next term is determined by multiplying repeatedly the same thing, okay? Whereas in an arithmetic sequence, the next term is adding the same thing to the previous term, okay? That's the big difference here. So just like with arithmetic sequences, we've got two ways that we can actually find like a term that's way down the road, okay? We can either keep multiplying over and over and over again, right? Which can get really boring and tedious. And if we could find a shortcut, wouldn't that be better, right? Like I'm all about shortcuts here. So if we could find a shortcut, that would be like option 2. We can construct a rule here. So if we construct a rule, what we need is we need the first term in the sequence, just like with arithmetic sequences. And instead of the common difference, now we're dealing with the common ratio, but it's the same exact idea here, okay? So similarly, we've got explicit and recursive rules, and we're going to construct them similarly to the way we did arithmetic sequences, except instead of doing addition, we're going to involve multiplication instead, okay? It's a slight tweak, but it makes a difference, okay? So here we are. We're looking at this 3, 15, 75, 375. So the first term is 3, and the rule or the common ratio, hopefully I did it right on this part, okay? I did 3 times what gets me 15? Well, that's 5, okay? So the common ratio here is 5. All right, so if I'm dealing with an explicit rule, again, here's another typo. You're going to do f of 1 times your common ratio to the n minus 1 power, okay? So f of 1 is my first term. That's my starting value, just like when we had an exponential function, right? A is my starting value times b represents my common ratio, and then instead of having like a, an x up here, in this time, n minus 1, again, n minus 1 means the previous term, okay? So if I'm looking for position 9, I'm going to look at the previous term, which is position 8, right? So 9 minus 1 is 8. So 3 times 5 to the n minus 1 power. That's how you write an explicit rule, okay? Because this is an exponential function. Again, 3 represents the first term or the starting value. 5 represents the common ratio or the rule of the sequence, okay? This should look really familiar to you. Now, as a recursive rule, it's a little bit different. Again, f of 1 is 3. The way that we would write it is f of n minus 1 times d instead of doing plus d, okay? So to do the recursive rule, you have to have 2 lines of data here. You always write the first term, and then you would have your sort of recursive rule after that, but you have to set the first term there, okay? This is very similar to what we did last time, right? So again, here's my explicit rule. Sometimes instead of saying f of 1, I would say a sub 1 times d to the n minus 1, just like that. Here we've got a sub 1 instead of f of 1. Same thing. This is my starting value. And then instead of f of 1 or f of n and f of n minus 1, I would do a sub n and then a sub n minus 1 times 5. This is just another way to write it. We're doing the same thing that we did up here. It's just another way to write it. Instead of saying f of x, we're saying a sub x or 1 or n or whatever, okay? All right, so we're going to do one example here. Again, all the guided notes are fully available to you online. Just go into Canvas, they're right there in modules. All right, so here's the sequence. First term, yep, -2. How do I get from -2 to +4? Well, I know that 2 times 2 is 4, but then I switched the sign. So I'm thinking my common ratio instead of +2 is actually going to be -2, okay? So if I wrote a recursive rule here, I would have to have 2 lines. First, I would have to say f of 1, or my first term. My first term here is -2. So I got f of 1 equals -2. And then my next line is going to be f of n is equal to f of n minus 1 times my common ratio, which in this case is -2. Okay, so here it is right here. For a recursive rule, you have to have 2 lines, which again, just like with arithmetic sequences, I much prefer the explicit rule. Okay, it's a little bit more direct. You don't need a lot of other information. You just need the position that you're going to. So just like with an exponential function, my starting value is -2. So I'd say -2 times, and then my common ratio, which is also -2, and then I would say to the n-1 power. Okay, so if I were going to find the 12th term in the sequence, instead of n-1, I put in 12 for n, so 12 minus 1, and then I just go ahead and solve it just like I normally would. Okay, you do that straight into the FSA calculator. It does a lot of work for you, and then you're good to go. All right, so that's geometric sequences, guys. Geometric sequences are just like exponential functions. Okay, I think I actually wrote that song. Oh, there it is. Geometric sequences are exponential functions. There it is. Okay, so that's it. That's it for the sequences. Please come to my office hours if you need any help. Otherwise, keep going on that work. Keep working on that homework, and I'll see you for the test.